Hi, this is Solomon. I'm an inventor and I like to innovate. The question is, what is innovation? Here we see from the Oxford Dictionary that innovate is a verb that makes changes in something established, especially by introducing new methods, ideas, products. For example, the company's failure to diversify and innovate competitively. So to innovate is really to introduce something that is new, especially in a product. So we continue to innovate new products. As an inventor, I need to think innovatively. And today I would like to tell you a little bit about how I think, as well as how to innovate. Now, an innovator is a curious person, and he usually asks a lot of questions. And there are 6 kinds of questions that you can ask. 1, where? We're going to talk about where, the question of where today. And second question is when, what, who, why, and how. Now, I'm going to teach how we can think in these 6 different ways. And today we're going to focus on the question of where. Now, when you think where, you're talking about spatial thinking. You're talking about, sometimes we call intuitive thinking. You think in terms of picture. You don't go through logical reasoning, but you kind of think in terms of what you see in your mind's eye, and you trust your gut feeling. And that's what I did when I was studying at MIT. I was able to think intuitively when I study subjects like electromagnetism, and I can literally see the answer right in front of me, and I put down the answer, and then afterwards I would try to verify the answer itself. So I was able to really derive answers to questions in electromagnetism intuitively, and can do a test very quickly. So today I would like to talk about a little bit about this process of thinking intuitively and spatially. Now, people like Einstein like to think spatially. For example, when he talked about special relativity, he think in terms of people riding on a train and flashing lights and seeing how space scale contracts and the time scale dilates, okay? So you can see that literally, and also in the case of general relativity, he was able to see how space and time can curve. The first question we can ask ourselves is, where are we in the universe? And we are right dead center in the universe. Every point in the universe actually is the center of the universe, because since the Big Bang, we are on the surface of a sphere, kind of, and then every point on the sphere is the center on the surface of the sphere. So as we see it, the center, if we put the sun at the center of the universe, we're on the 4th planet out from the center, and then there are other planets, and we are on one arm of the Milky Way galaxy. Now, this distance scale here is compressed, meaning it's logarithmic. So as you go further out, the distance increases actually logarithmically as the distance you see on this picture. Exponentially increases exponentially. So the one arm of the Milky Way becomes very large, and then it goes further away, and this is the Milky Way galaxy. And then there are other galaxies that are at quite a bit of distance. For example, I think this one would be the Andromeda galaxy, which is the closest to us, and a few million light years away from us actually. And then going further out, you can see the other galaxies, and then you can see the cosmic cluster of galaxies form like a string. And then further out here, you are looking actually into time. As you go further out, you're looking into the past, because light takes a certain amount of time to travel from this point to this point. And here would be close to the Big Bang, about 1 million years away from the Big Bang. Where you have a very high temperature, and beyond that you have the dark ages where light cannot propagate because all matters are ionized, and beyond that you can see almost into the Big Bang further out, okay? But we can't see that largely because light becomes opaque beyond this point. All right, so we're living in a very exciting time whereby we have a lot of different kinds of telescope to peer into the past and in effect looking into a very distant past and also a big distance away. Now, from the center where we are to the edge of the universe of the visible universe, we're talking about something like 50 billion or more light years away from us. So it's very big. Now, the Big Bang was about 14 billion years ago. So how could the distance be so much bigger, 50 or more billion years out? It's because this Big Bang is continuing, is expanding. So space actually is being stretched out larger and larger. And so they move away at a fairly high speed away from us at a fraction of the speed of light away from us. So that distance traveling to the edge of the visible universe is much bigger than 14 billion light years, largely because this sphere is expanding, okay? Now, when we think spatially, we can think in terms of directions. This is from a human experience, the earliest kind of experience we have. We talk about the east where the sun rises and the west where the sun sets. And during the noontime, the sun is directly south of us if you're in the northern hemisphere. And so we usually associate east with the beginning of the day and west as the end of the day, whereas south is usually where we feel warmth and the north is where we feel chill. And so that sort of experience directs us to formulating 4 directions, the east, the west, and the north and the south. And there are 2 more directions. One is up and down. When we jump up, we fall down. So that is due to gravity. So from a human experience point of view, our notion of 3-dimensional space is shaped by our experience with the sun, as well as the experience with gravity. So there are 3 dimensions in our experience. So since the Middle Ages, we have Cartesian Descartes formulating the Cartesian coordinate in terms of these 3-dimension directions. So you can represent east as the coordinate, the x coordinate, the north, the south as the y coordinate, and the up and down as the z coordinate. So you can represent every point on Earth in terms of the x, y, z coordinate. It could be that this is the 0 coordinate and this is the surface of the Earth, and this is up and down, and this could be Greenwich, where you have a 0 longitude and then you increase the longitude this way and you have a latitude this way, okay? So you can represent your presence on the surface of the Earth in terms of an xy coordinate, and you represent the altitude, where you are up in the z coordinate. So you can represent that as x, y, z. Now, we live on the surface of the Earth, which is obviously not a flat surface, it's a curved surface. And so, but today we're going to talk about, first of all, the distance between 2 points in this 3-dimensional Cartesian coordinate. And for that, this is one of the earliest mathematical theorem that people have proved. And I like to think about that when I was a very young person, to prove the theorem called the Pythagoras Theorem that was invented. Pythagoras wasn't the first one to really state the Pythagoras Theorem, but I think he was the first one to prove the Pythagoras Theorem. Now, what is the Pythagoras Theorem? What it says here is that if you have a triangle with corners capital A, capital B, and capital C, and the opposite of the angle A is the length A, and the length B, opposite to B is length B, and opposite C is length C. Pythagoras theorem states that A squared plus B squared is equal to C squared. And it's one of the most profound statements, and I was growing up, I was trying to prove this many different ways. And today I'd like to cite a proof that is very intuitive. It's not due to me, but it's very intuitive. Now, if you look at the triangle here, what you see here is there are actually, how many triangles can you see? Well, you have one triangle here, two triangles here, and three triangles altogether. Now, the A, B, and C are the hypotenuse, or basically the longest side of the triangle. For example, A is the longest side of this vertical angle triangle, whereas C is the hypotenuse of the largest triangle that you can see here, as well as B being the hypotenuse of this smaller, the smallest triangle over there, okay? Now, if you think about it, since they're all the hypotenuse and they're similar triangle, meaning that the angle, one of the included angle of the triangle theta, this is theta and this is theta, and this theta is common to this triangle and this triangle, whereas this theta is for this smallest triangle. So if you know about that and you think in terms of the area of this triangle, it should be proportional to the square of the length of the hypotenuse, right? So what you have here is that this triangle has area that is proportional to a squared, because a is the hypotenuse length of this triangle, and c is the hypotenuse length of this triangle, and therefore the area here should be proportional to c squared, whereas this hypotenuse of this triangle here, b squared, should be proportional to the area here. So what you have is that since these two triangles added together forms a larger triangle, so therefore you would have a squared plus b squared equals c squared, because a squared, the area that is proportional to this triangle, and b squared proportional to this triangle adds up to c squared, right? So therefore you would right away arrive at the conclusion that a squared plus b squared is equal to c squared. Now this is rather intuitive and also profound, largely because you're thinking in terms of space, because area should be proportional to length squared. And since you have three similar triangles, and therefore the principle of proportionality and also the principle of addition applies, and therefore you have the proof of the Pythagoras Theorem. This is a very easy proof. Now, why is Pythagoras Theorem very important? Well, it has been very important to people building the pyramid or building the Great Wall of China and other structure, largely because all architects rely on Pythagoras Theorem in order to build structures. Now, but it's more profound than that. It's not just a matter of building the pyramid or building walls, but rather it's a measure of distance. Why is it a measure of distance? Now, if you look at the Cartesian coordinate representation of location in space, where you have one point represented by the x, y, z coordinate, and suppose this is called a point P1, and you have another P2, and so you can have a subscript of P1 being represented by the coordinate x1, y1, and c1, and the other point being x2, y2, and c2. So what you have is you can measure the distance between P1 and P2 out there by subtract off the coordinates. For example, it would be x2 minus x1, the whole thing squared, y2 plus y2 plus minus y1 squared plus c2 minus c1 whole thing squared would be equal to the distance between the 2 point P1 and P2 squared. Okay, so it's a very convenient way. The Pythagoras Theorem actually allow us to calculate the distance between 2 points in very easily. Okay, you just subtract off the differences in each of the three coordinates and square that quantity, add all these square differences together, then you have the square of the distance between these 2 points P1 and P2. So it's a calculator of distance. Now it's not, this is very profound, largely because what it says here is that somehow if you represent distances by differences of the coordinate, then the sum of the square of the differences of the coordinates is equal to the distance between the 2 points. Now, we're going to revisit this next time when we talk about time, because time is a very special dimension We call it the imaginary dimension, but I'm not going to talk about this now largely because that would be jumping ahead of myself. Now, in terms of what you saw earlier, the representation of the universe in terms of a Big Bang expanding sphere, it's not very natural to talk about the XYZ dimension. It's far easier to talk about a polar coordinate. What is a polar coordinate? For example, in a two-dimensional XY space, you can represent the point M either as AB, meaning that this is A and this is point B. This point is COB and this point is COA, and this point is AB. So you can simply add these two vectors. If you call a vector being an ordered pair of two coordinates, you add this COB plus A0, you get AB. Now, if you add them together, you get the point M. But there's a better way, I think it's a more natural way, to represent the point M by means of a polar coordinate. What is that? Polar coordinate says that you are at a distance of r, or radius, from the center at an angle of theta from a somehow arbitrary chosen axis. So this is represented in terms of a radius r and an angle theta. So that's called a polar coordinate representation. If you know a little bit about trigonometry, you will know that A is equal to R times cosine theta and B is equal to R times sine theta. And this is very easy to convert between the Cartesian coordinate and the polar coordinate that way. Now, today I would like to tell you about my invention of the spiral turbine and using polar coordinate, okay? And as an illustration of how to think intuitively. Now, if you think about the circle, another very wonderful number associated with pi, basically the circumference of the circle is equal to pi times the diameter of the circle. That's another number that I think a lot about, pi. And now, a circle, in terms of polar coordinate, is basically represented by r equal to a constant, where r is radius, because no matter how much theta you have turned, the radius is still r. Okay, so it's a circle is a constant radius object in the polar coordinate. Okay, so that's very simple. Now there's another spiral called the Archimedes Spiral, and the Archimedes Spiral is used by who else? Archimedes, to really do a lot of interesting things like creating water pumps. It is described by in the polar coordinate as a trajectory illustrated by this red curve, whereby the radius increases linearly with the angle term. So this is theta equal to 0, then r is equal to 0 at the beginning, and then as it increases, as you turn more and more, this becomes larger. As you turn an angle of pi, and then 2 pi, it would practically doubles. So every time you turn an angle of pi, we call it pi radians angle, you increases, the radius increases by the same amount. So that's called Archimedes spiral. And therefore, it is a kind of spiral that is used a lot in engineering. There's another spiral that is by the name of Bernoulli, also called the Exponential Spiral, discovered by Bernoulli as he observed in nature many of the spiral shapes has an exponential shape. Now, how does it work? You have an exponential function, f equal to e to the x, and in polar coordinate, what you have is the radius r is equal to e to the a e to the b times theta. Where theta is a term in polar coordinate. R is the radius, so the radius increases as a constant a times an exponentially increasing function of rate b theta, okay? Theta being the angle term. Now, this Bernoulli spiral was so beautiful, and I'll explain why later, that Bernoulli himself wanted that to be marked on his gravestone. And unfortunately, the person didn't understand what the exponential function is, so he marked the gravestone with an Archimedes spiral instead. Really a ugly shape when compared to the exponential spiral. So what we have here is a spiral that occurs very often in nature. So if you observe in nature, the biggest object in the universe, basically galaxy that we saw at the beginning of this talk, has spiral arm that is exponential in shape. Increase the distance from the center of the galaxy, very often the black hole, will be increasing exponentially as the angle turns. Now, you have other examples. Some pretty famous ones include the example of a sunflower pattern, also have exponential spiral shape. Also, the shell of a nautilus also have an exponential spiral shape. You can see that here. The distance increasing exponentially. So exponential spiral has something to do with growth. The growth of a sunflower or the growth of a nautilus shell, okay? And as also another very famous natural kind of object called a hurricane, for which you can see the spiral arm also have an exponentially increasing distance from the center. Now, there's a good reason for that, and a lot of that has to do with a phenomena we call self-similarity. What is self-similarity? Self-similarity corresponds to, if you look at this spiral shape, no matter whether you turn in terms of theta, if you look at it from a different angle, it looks the same. And also, as you zoom in and zoom out of the spiral, it also looks the same if you allow this to continuously spiral towards the center. So self-similarity is very good because it's a form of symmetry. It's a most symmetrical shape or self-similar shape in the polar coordinates. What it is that there's several reasons for that. It's self-similar largely because of the angle at which this makes with this tangent. If you look at, for example, this angle here, it has to do with, it's a constant angle. For example, if you look at how an eagle will fly towards the center to catch the prey, it follows the shape of an exponential spiral, largely because the eagle literally will caught its own eye, the eagle's eye, at an angle that is different from the flight path. Okay, for example, if the eagle is flying this way, and somehow the eagle turns its head to look this way, or literally the eyeball turns at a certain angle, then the flight. So what happened is that if the flight path is turned off at an angle phi that is equal to the inverse tangent of 1 over b in my earlier formula, that constant angle will force the eagle to fly towards the center. Okay, so this is one way to characterize an exponential spiral. It's basically that you can think about an eagle for which it cocks its eye towards the center, and then there's a flight path that is slightly tilted towards this the eyes, this line here. Okay, so we fly inwardly towards the center that way. So let's go back to the hurricane, which inspired my exponential spiral. I actually didn't come to the conclusion that I should build the gas turbine in an exponential spiral shape. I did a lot of experiments to find that out. Actually, I started with an Archimedes spiral, and then I implemented turbines using the exponential spiral, and find that the exponential spiral turns better. Very much like the hurricane actually is more powerful when the wind blows from the outside to the inside in a logarithmic radius. Okay, it increases exponentially as you go outside. It decreases logarithmically towards the center. I think that is what geometric thinking is all about. Geometric thinking is about thinking like you see a picture of gas flow. And you ask a very basic question of what is the best way for gas to flow to liberate its energy? Because I want to build a gas turbine whereby heated up and pressurized gas would be yielding its heat energy or pressure energy into motion energy. And after long thinking, I come to the conclusion, both in terms of thinking and also in terms of experimentation, that the exponential spiral, and not only the exponential spiral, but the tapering exponential spiral. So you may be going on towards the inside, but as you go towards the inside, the volume is, the vertical distance is increasing exponentially on you. So that will liberate the energy of the gas in terms of heat and turn that into motion energy, and therefore will be able to convert energy from heat into motion. All right, so I hope that you understand how I think in terms of intuition. What I mean is that in order to be innovative, you always have to ask the question of where, meaning that you discover the relationship in terms of the spatial distances of these things, of the different objects in which you're considering, and also how they interact with each other spatially. And I think it's a very important way to learn how to innovate is by means of, we call the process of design, because design involves the process of thinking spatially, and then you will be able to design things that are useful to other people, because after all, we are all architects of our world. We create buildings, we create engineering objects like turbines and other stuff. And also, I also build electric motors, and I like to think spatially in terms of the flow of the electromagnetic field and also how forces act on each other. Okay, I hope you understand this aspect of Solar Man thinking. Until next time, this is Solar Man.